Hello, dear students. This is Shakil, and today we are going to discuss circular motion from A2 physics syllabus. So, well, about circular motion, everyone knows what is circular motion. It's the motion of object along a curved or circular track. So, what we have to study in it is basically this topic of kinematics or mechanics because it involves movement. So we have to study about various terms, let's say about the radian, angular displacement, distance, angular speed, and then the equations for angular speed. And we have to study about centripetal acceleration as well. So let's talk about it. Well, before we go into circular motion, we have to recall what is linear motion. Linear motion is motion along straight line. It can be horizontal linear motion, it can be vertical linear motion. Like this is horizontal linear motion and this is vertical linear motion. Well, the terms that we discussed in AS physics was distance, displacement, speed, velocity, acceleration, and force. All above we have studied in kinematics and dynamics in your AS level syllabus. Now, about the circular motion, it's the motion of object along curved or circular track. Well, it can be horizontal track, well, that is parallel to Earth. It can be perpendicular track, that is 90 degrees to Earth plane. So we have to study the same terms about circular motion, distance, angular displacement, angular velocity, angular acceleration, and centrifugal force. Well, let me tell you a few examples about circular motion. As you can see in the diagram, planets orbiting the sun. The planet orbiting sun, they are executing circular motion. Moon around planet, well, it's again circular motion. Electrons around the nucleus, all the electrons which are moving around the nucleus, they are performing circular motion. And the car taking a sharp turn as well. And some swings as well, they move along circular track. Okay. So, well, we have to study about the terms related to circular motion. Of course, when the object is moving along circular motion, it is covering some distance. So there are like two types of distances. The first one is along complete circle. Well, if the object has executed one complete round trip, then the distance that it has moved or covered is equivalent to circumference of the circle, and that is 2 pi r, where r is the radius of the circle. But if it is along the arc of the circle, like it is not a complete circle, let's say it has moved through this much of the distance, then this is the S distance which you have to find. This is the center of the circle. R is the radius of that curved track, and theta is the angle between the two positions that object has executed. Like say, initially object was at t0, it was over here, and after time delta t, it reaches over there. So of course, it subtended an angle theta between the two positions. R is the radius and S is the distance, which we have to know, which we have to find. So from the definition of maths terms, arc length S equals radius into angular displacement between the 2 points. So S equal R theta, a famous equation. All the math students must have a knowledge of this before as well. So the theta is the angle which we measure in radian, not in degrees. Okay, the next term is angular displacement, theta. Well, the definition is angle subtended at center of circular track between any two positions of the object is known as angular displacement. Let's say if an object is moving along circular track and, well, let's say it was initially at this point, time 0, then it moved and it reaches at this point after time t. So of course, it has subtended an angle theta between the two positions, right? If it is perfect circle, the radius in both the cases is r. So, well, this angle theta subtended at the center of circular track between any two positions of the object is known as angular displacement. So remember, in linear motion, we studied displacement having unit meter, but in circular motion, we studied angular displacement having unit of radian, and it is in terms of angle. So theta equals arc length divided by r. So its SI unit is radian, and some other common units are degrees, cycles, revolutions. Well, for one complete rotation, the angle theta at the center is of course 2 pi radian, or it is equal to 360 degree, or it is equal to one rotation. So as we say that S equals R theta and theta equals S by R. So just putting the value for one revolution, S, which is arc length, is 2 pi R, and radius is radius, so R cancel away. So you got to prove that in one revolution, the angle is 2 pi radian. The next term, is angular velocity, which is denoted by omega. Well, like linear velocity, which is rate of change of displacement, it is rate of change of angular displacement. Well, the omega is delta theta, which is change in displacement divided by time. So the unit of change in this angular velocity is radian per second. This is SI unit, and some other common units are degree per second, revolution per second, rotation per second, or cycle per second. Well, for one full rotation of the object, the change in angle is 2 pi radian, everyone knows that, and the time that it took is equal to time period. So when we replace these values, like we're going to replace these values over there, this value over there, so you'll get the new value for omega, which is 2 pi over t. Well, and then we know that 1 over t equals to frequency, so this can be modified as omega is 2 pi f. Okay, this equation is in terms of time period, and this is in terms of frequency. So again, the direction of omega is along the axis of rotation. It can be either clockwise or anti-clockwise. Well, when an object is moving along circular track, it's having two types of velocity. One is the angular velocity omega, which is around the axis, and one is the linear velocity, which is tangential velocity, which is tangent to that point. So we have to make a relation between linear velocity and angular velocity. Well, linear velocity is always tangent to the circle, always tangent to the circle, like this, as shown in the diagram. If it moves to this distance, of course, it is over here. If it is moved to this distance, then tangential velocity is like this, and over here, tangential velocity is like this. So at all the points, the tangential velocity is perpendicular to the force. Well, about the angular velocity is always along the axis of the rotation. So we have to develop a relation between angular velocity and linear velocity. So let's start with linear velocity. We know that velocity is distance over time. And when the object has executed one full rotation, the distance that it has moved is 2 pi r, because that is the circumference. And the time that it took is capital T, time period. So just fill in these values over there. So at place of D, 2 pi r, at place of small t, it is capital T. So we know that 2 pi over T is actually equal to omega. When we replace that, we got V equals R omega. This is the famous relation between linear velocity and angular velocity. Usually for a motion, R is constant. So then V proportional to omega. It means if you increase V, omega would also increase, and vice versa. Well, the next term is angular acceleration. It's again as simple as the simple acceleration. Simple acceleration is rate of change of velocity. It is rate of change of angular velocity, right? Okay, angular acceleration is rate of change of angular velocity, and its unit is radian per second square. This is a vector quantity. Well, the derivation of angular acceleration are not in the syllabus because the values are given in the data sheet. So we have to start it from the first equation is angular acceleration equals linear velocity and angular velocity, like product of them. And then you know that V is equal to R omega. So substituting these value over there. So we got this relation, which is also given in the data booklet, V equal R omega square. Here, of course, R is the radius and omega is the angular velocity. Again, we know that omega is V by R, so substituting its value over there and simplifying it will give you another relation in terms of linear velocity, which is V squared by R. So what you can do is you can express angular velocity in terms of angular acceleration in terms of angular velocity and angular acceleration in terms of linear velocity as well. Well, the most important term is centrifugal force, because this is the resultant perpendicular force acting on the object in order to move it along a circular or curved track. So this is the force due to which object changes its direction. Well, let's look upon some features. First one is it is the resultant of many forces or it can be a single force. Number two, it's always towards the center of the circle. Wow, this is important. Number three, it is responsible for changing the direction of the moving object. Remember, this force would not move the object, but this will change the direction of the moving object. Well, about the equations, of course, we have to use them in the numericals. The famous Newton's second law is used. F equals ma, where F is the resultant force, which I mean the centripetal force here, m is the mass. And as you know, acceleration has got two values. So when you substitute those two values, you got two new expressions for centripetal force, which is mr omega square or mv squared by r. Okay, well, let's look upon some cases or some examples of circular motion. So there are two types. One is the horizontal circular motion, and the other one is vertical circular motion. Okay, so in horizontal circular motion, first we'll study about a stone tied to the rope, then car taking a turn, then aeroplane taking turn in air, car on inclined racetrack, planet's round star, and the conical pendulum. And in vertical circular motion, we'll study stone tied to rope and wheel along vertical track and car on a hump bridge. Well, what are our objectives in all these 8 examples? We'll be finding expressions for centrifugal force and acceleration. Well, and how we can do that. First, we'll draw the free body diagram. We'll label all the forces. We'll trace the forces acting along the line between the center of the track and object, and even beyond the object. Then we find the resultant force by this expression, force towards center minus force away from the center, along the line, of course, joining object and the center. And then F equals ma, A equals F by m can give us the acceleration expression. Well, let's now work on stone tied to a rope and wheel horizontally. So you know that this is, let's say, the rope, and this length is r, or it can be l, and this is the stone of mass m. Its weight is acting vertically downward, like this is 90-degree angle. So now we have to find resultant force, which is force to center minus force away from center. So if we mark the forces, the tension is always towards the center and the weight is downward, like tension and weight are perpendicular to each other. So you cannot resolve any of them because they're perpendicular. And then you have to make a line from center to the object and even beyond that. So only one force is on it, which is T. So force towards center is T, and there is no force away from the center. So it means that the centripetal force here is equivalent to tension in the rope. So centripetal force is mr omega square, that can be equal to T, or centripetal force equal to mv squared by r, that can be equivalent to T. So you can use this expression to find anything related to this movement. Okay, the next one is car taking a turn on a round track. Well, as you can see in the diagram, the car is moving around a circular track. Well, let's imagine car is at this point. So at this point, it's a force must act towards the center, and that is actually the friction between tires and road, and no other force acts opposite to it. So that's why the force towards center is friction and no force away from the center. So that's why the centripetal force equal to friction, or we can say mr omega square equal to friction, because this is again the horizontal case as well as we studied before, or it is mv squared by r equal this. Well, this is a bit tricky as the top view is shown. Whenever car is taking a turn, let me make this like this is the center of the turn and car is over here. Okay, so I was telling you, I was muted for a time. I was telling you that let's say this, if this is the car moving towards the center, so its weight and our normal reaction are perpendicular to the friction. So that's why I will not consider that. So but you have to make a dotted line between center of the object and beyond that. And when you are done with labeling all the forces, so when you look at how many forces are acting along the line, which line? This line. Then you found that only friction is acting on it. That's why this friction is equivalent to centripetal force in this case. Well, aeroplane taking a turn in air. Well, a smiling aeroplane is there. So let's label the forces. Don't worry, buddy. Well, it's taking too much load. That's why I guess it is exhausted because aeroplane have to travel a longer distance. So the weight is downward and the lift force acts through the tail. Like this is the tail and this is the lift force, L. L is the lift force due to air. So if it is moving horizontally, so the weight and the lift force will be equal to each other. So it is maintaining constant height, right? Okay. Now, if it is taking a turn, like in this case, this is the center of the turn, and this aeroplane is actually going like this. So what we say is that its weight is downward, but as it is taking a turn, so the normal reaction force always passes through this tail. So this is the lift force, like the lift force always passes through the tail. So it displaces at an angle of theta. So now what you have to do is you have to resolve this lift force. So this component is L cos theta, and this component is L sine theta. So now you have to label the forces between center of the object and the circle. So when you look at this line, that how many forces are there, the only force that is on the line is L sine theta. And there is no force away from the center. So that's why we say that the centrifugal force is equal to L sine theta. But one more thing over here is weight equals L cos theta, right? So this is the centrifugal force, like mv squared over r is L sine theta. Okay, moving forward, car moving on inclined track. Well, I tried to draw the car on inclined track. This is the theta, this is the center of the turn, and this is the car actually. So let's say, you know that whenever you must have seen the car race on the circuits. So the outer edge of the road is taken above so that the cars can move at higher speed without brakes are being applied. So in this case, we have to see that how the car can manage to move faster when it is set in a circular track, because on flat road, they can't do that. On flat road, as we have a usual experience, whenever we reach a turn, or we have to enter in a roundabout, or we have to take a U-turn, we have to slow down the car to a safe value so that we can easily take the turn. But in the circuit car race, the outer edges are taken upward, the track is bent, so the car drivers can move faster and faster while taking the turns. Well, so of course, there is some additional centripetal force required for that, and that is provided by the component of the weight in this case. Okay, the normal reaction force is like this, right? So now again, you see that normal reaction force is having an angle theta with the line of action of weight. So when you resolve it, so this is like r cos theta, and this component which is towards center is r sine theta, right? Okay, so now we say that the force which is towards center is r sine theta. But one more thing is the weight is equal to r cos theta, right? So what we can do is we can substitute the value of r, like r is w over cos theta. So what we can do is we can substitute its value over there. So the centripetal force will become w over cos theta into sine theta. So this would be w tan theta. So finally, we can say that the centripetal force is w tan theta. So this is the additional force that is provided for this car so that it can move at higher speed. So the one thing is the centripetal force is the r sine theta, this is in terms of r, or the centripetal force is equivalent to W and theta. This is in terms of weight. So both these are can be used, and this is actually the derivation for this, that centripetal force equals W tan theta. Okay, let's move on the planets around sun or moons around the planet. You know that all of their motion is circular. This is Earth, this is sun. So sun is pulling it with a gravitational force, and there is no other force. So we say that the centripetal force is equal to gravitational force between Earth and sun. So we'll discuss that in detail in the next chapter of gravitation. Like this. Okay, moving forward to next case, which is the conical pendulum case. If we talk about a simple pendulum, so there is a difference between simple pendulum and conical. Okay, the conical pendulum actually moves along a horizontal circular track, like the way you can see in the diagram. And if we talk about the simple pendulum, that moves along like one curved track, and that keeps on swinging along that curved track. So that is actually the basic difference between the conical pendulum and the simple pendulum. So what we have to do is, as you can see, that this pendulum is moving along circular track. So we have to see that how it is moving along circular track. What are the forces that are responsible for moving this object along circular track? Okay. After that, we'll get back to this. After that, we have to study about the vertical circular tracks, like the car moving on the hump bridge. And then we have to look about the stone case or the object case, which is moving along the circular track. And then we will be solving some past paper questions. Okay, so let's get back to the conical pendulum. I was telling you that the simple pendulum, if it is like this, and it just swings like this. So that is what simple pendulum is about. So this is simple pendulum. Okay, this is conical pendulum because it is moving along a horizontal circular track. Horizontal circle. Okay, so what we have to do is, let's imagine that it reaches at this point and the rope is, let's say, over here. Okay, so what we have to do is we have to label the forces. Its weight is acting downward, tension is that way, and well, this is the angle theta. Well, maybe we can stop it. Yeah, not exactly at that instant. Well, last try. Well, okay, let's just make it like this, like the pendulum is over there. So its weight is acting vertically downward, tension is that way, and it is displaced at an angle theta over there, right? So it's better to trace it because then we have to move the pendulum as well. Okay, so now what we'll do is we'll make a line of action of weight. Like this dotted line is a line of action of weight, and its angle is theta, as these are alternate angles, so these are equal. So what you'll do is you'll resolve this t. So this component will be again t cos theta, and the component towards the center of circle, because this is the center, is p sine theta. So now we'll see like this is the center and this is the object, so we make a dotted line. We always make a dotted line, and then we see that how many forces are acting on this line, like how many forces are acting on this yellow line. So we can see that only one force is acting. So our expression is resultant force or centrifugal force is force to center minus force away from center. Okay, so force to center is p sine theta, and force away from center, no. So it means we say that centrifugal force is equivalent to p sine theta in this case. Plus, one more thing, that the weight is equal to T cos theta over here. So what we can do is, from here we can make T as the subject, so it is T is W over cos theta. So what we do is we put it over there, so the centrifugal force equals W over cos theta into sine theta, and finally centrifugal force equal W tan theta. So this is the same expression we got for the previous two cases. Centrifugal force is W tan theta. Well, in this case, it is W tan theta. And actually, in this case, it is still equal to same, right? So for all of these three cases, centrifugal force is W tan theta. Okay, now let's talk about car on a hump bridge. This is a car, and it is on the top of the hump bridge. Well, if we label the forces on it, weight is downward and normal reaction force is upward. So as this is the center of the hump bridge, so, well, we have to label the forces acting along this. We have already labeled them. So we'll say that, well, the resultant force is always towards the center. Resultant force is always towards the center. So resultant force is force towards center, which is W in this case, minus force away from center, which is R in that case, in this case. So we'll say that centrifugal force equivalent to weight minus R, or we can say that weight is equivalent to mv squared by R plus the normal reaction force. So that's the expression over here. Well, about the stone or the object moving along the circular track, well, let's see. First, we have to look for it at the bottommost point. So let's say, firstly, it is at the bottommost point. So first is bottommost. So when it is at the bottommost point, we have to find the expression for centrifugal force, or we have to find the expression for tension. So we'll first label the forces. Weight is downward and tension is upward. So as you can see that this is the center and this is the object. So we have to look for how many forces are acting along this line. And as resultant force is always towards the center, so the force towards center would be the bigger force as compared to force away from the center. So centrifugal force will be equivalent to T minus W. And centrifugal force here is mv squared by R, which is equal to T minus W. Or T over here is equal to centrifugal force plus weight. It means that this is the maximum tension that the spring can experience because it is sum of the two forces. So when the tension is maximum, it means that the rope is most likely to break over here. The string or rope is most likely to break because, you know, whenever you have to break the string, the tension force should be maximum at that point. Okay, so now we have to go to the other point. Let's say at some angle. At some angle, and let's say that angle is, you know, well, that angle is maybe this one. So, well, now if the object reaches at this point, it is, of course, at some angle theta from the original position. We have to again label the forces. So let's label them. Weight remain downward, tension is that way. So as weight is displaced from the tension, so you can resolve weight. So when you resolve weight, this one is like W cos theta. Okay, now again, what you'll do is you'll make a line between the center and the object, and you have to see that how many forces are acting on that line. So we say that the resultant force, which is centrifugal force, is equal to force towards center, which is again the tension, minus force away from the center, which is W cos theta. So that is your second expression, right? Okay, now let's move on to the third expression, which is object is like at the horizontal position. And let's say the object is reaching another position which is perpendicular to the start. Well, I have to stop it again. Okay, last try. No. Well, one more, maybe. Okay, let's see that this is the new position of the object. Like this was the first position, this is the second position, and this is the third position. So at third position, you have to label the forces. Weight acts vertically downward, tension is that way. And then you have to see how many forces are acting along this line. So as only one force is there, which is force of tension, so you will say that in this case, centripetal force is only equal to tension. Well, let's move on to number 4 now, which is the topmost point. The object has just reached the topmost point. Okay. Okay. Well, so this is the topmost point. Object reaches at the topmost point. So when it is at the topmost point, you have to label the forces. Its weight is downward and tension is also downward. So now both the forces are downward. So as resultant forces towards the center, so we say that both forces are in the same direction. So you'll add them. And over here, tension will be centripetal force minus weight, which is the minimum tension. So the minimum tension is always at the highest point of the circular track. Now let's look upon some past paper questions from this topic. Well, there's a horizontal flat plate and there's a mass placed on it at a distance d from the center of the rotation, which is moving clock and clockwise direction. So what you have to do is a small mass is placed on the plate at distance d from the axis of rotation. The speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide off the plate. Well, when the mass slides off, it will move in this direction. The maximum frictional force between the plate and the mass is given by this expression. So this is actually the frictional force, which is providing the centripetal force, and it is actually acting towards the center, right? Okay, so this is 0.72 W, and the distance D is 35 centimeter. W is, of course, the weight. What you have to do is you have to determine the maximum number of revolutions for the plate per minute for mass to stay on the plate. This is actually a 5-mark question. Okay, you have to find number of revolution per minute. Revolution per minute. It means actually you have to find omega, but you have to find it in revolution per minute. Okay, let's solve it. You know that F is 0.72 W, and this F is actually providing centripetal force, which is mr omega square, and this is 0.72 mg. Well, as m is same on both the sides, so m will be cancelled away over here. And this R is 35 centimeter. So this is actually 0.35 meter. So this is 0.35 omega you have to find, and 0.72 into 9.81. What you'll do is you'll find omega from here. And that omega will be in radian per second. So let me find out the calculator so that we can solve it. Okay, so it is 0.72 times 9.81, and you have to divide it with 0.35, and you have to take a root of it. So it is 4.49. So it means omega is 4.49 radian per second. But they are demanding the answer in revolution per minute, right? Like the way over here, revolution per minute. Okay, and this answer is radian per second. So what you have to do is you have to convert that into revolution per minute. So, well, how we'll do that? It is like 4.49, and well, like you have to convert this radian into the revolutions, right? So we say that in one revolution, angle is 2 pi radian, right? So in 4.49 radian, how many revolutions will be there? So that will be x. So you'll be cross multiplying them, and the x is coming out to be 4.49 divided by 2 pi. So it is actually equivalent to 0.72. Now this is in 1 second, right? So this is like revolution per second. Now you have to convert that into minute. So, well, if this is in 1 second, so how much will be in 60 seconds? So that will be 42.89. So you'll say 42. So 42 revolution per minute is the answer over here. Well, let's look at the next question. There is a disk rotate at the constant angular speed omega. This is disk. This is the disk, and it is being rotated like this. And then there is light coming from here, and its shadow just keep on vibrating up and down on the screen. So that is executing, let's say, the oscillatory motion. So what you have to do is the disk radius is 12 centimeter, and it is rotating with a speed of 4.7 radian per second. So you have to determine the shadow, or the shadow on the screen, the frequency of the oscillation. Like frequency of the oscillation means that the shadow is actually moving up, down, up. It is oscillating over there. So what is the frequency of the oscillation? The radius is given, and the omega is also given. So you know that omega is equivalent to change in displacement over time. It is like 2 pi. Well, in this case, we can't use that actually. So what we have to do is we have to find the frequency. So as omega is 2 pi over t, and it can be 2 pi 1 over t, and it can be 2 pi into f. So omega is actually 2 pi f, and f is actually omega over 2 pi. So omega is 4.7 over 2 pi. So if you divide 4.7 with 2 pi, so you will get the answer, and that is 0.747. So its frequency is 0.75 hertz. Well, you have to find its maximum speed. So speed is C equals R omega. So speed is R. R is the radius, which is 12 centimeters, so 0.12, and omega is 4.7. So you'll do the maths. 0.12 into 4.7, so you got 0.564. So 0.56 meter per second is its maximum speed. Well, let's do one more question. This is a stone of weight 3 Newton, and it is glued with this rod, and the length of the rod is 85 centimeter. It is given, and it is being whirled along this vertical circular track, right? And the glue fixing the stone snaps when the tension is 18 newtons. So the glue snaps when the tension is 18. So of course the tension is maximum at the bottommost point. So glue snaps over here, and the object will move to this point, because object always moves along the tangent to that point. So for the position of the stone at the glue snaps, on the dotted circle, mark with the letter S the position. So this is the point, because tension is maximum at bottom. So this is where the object, the rope can be broken or glue can be snapped. And you have to find the angular velocity. That's quite simple. Angular velocity will remain the same everywhere. So you'll choose a point at the bottom. So let's label all the forces. Weight is downward, tension is upward, and centrifugal force is always towards the center. So we'll say centrifugal force is tension minus weight, right? So centrifugal force is mr omega square, and tension is how much? 18, and weight is how much? 3. So it means mr omega square is equal to 15. Furthermore, you have to find angular speed. So it is like 15 over mr. And then, well, 15 over how much is m? Well, m is like p divided by 9.81. So it is 0.306. 0.306 is the mass, like W is mg, and m is w by g. So w is 3 and g is 9.81. Okay, and well, the value of r is 85, so it is 0.85, and then you have to take root to find the angular velocity. Well, that comes out to be 7.6. So 7.6 radian per second is the speed. Well, let's move to the next one. A telescope gives a clear view of distant object with angular displacement between the edges of the object is at least this. Well, it means that if this is a telescope and this is the object, so between the edges, like this is the object and this is the telescope. So if this angle theta is 9.7 times power minus 6 radian, then you can see the clear view of this object. Well, the moon is approximately this much away from the Earth, and you have to find the minimum diameter of the circular crater on the moon surface that it can be seen through the telescope. Okay, so well, the distance is 3.8 into 10 to the power 5 or 10 to the power 8 meter, 5 kilometer, and I've converted that into meter. So this is the distance, and you have to find this diameter of the crater. So it is actually S equal R theta, S is D, which is the diameter, R is the distance, which is 3.8 into 10 to the power 8, and theta is the angle, which is 9.7 into 10 to the power minus 6. So you get the answer. So it is 3.8 into 9.7. So, well, it is 3686 meter, or you can say it is 37. It is in kilometers. So you'll say it is 3.69 or 3.7 kilometer. Well, let's move to the next question. A ball is moving along a horizontal circular track having a radius of 14 centimeter in the bowl, and this is the ball touched with the wall of the bowl and its weight is downward and odd normal reaction force, and this is the line which is joining the ball to the center. So what you have to do is you have to show that the weight is equivalent to F tan theta. So how you do that, you'll of course you have to resolve this is the center, so you will resolve R. So this is R cos theta, and this is R sine theta. So as the centrifugal force is always towards center, so you will say that the centrifugal force is R cos theta, but you will say that the W is equivalent to R sine theta. So again, you will do the math. You have to replace this R. So R over here is F over cos theta. So you put that over here. So weight is F over cos theta into sine theta. And you know that cos over sine over cos is tan. So it is W equal F tan theta. Okay. Thank you so much, students. I'm going to share the worksheet in the WhatsApp group. So you have to solve some questions, but after viewing this video and making your notes. Thank you so much. We'll see you in the next topic. And the next topic is the gravitational field. So this is our simply gravitation. I'll be posting this video soon, inshallah. Take care, everyone. Have a nice day.